we can.
Yes, ma'am.
You can. Okay.
Good evening, ma'am.
So, ma'am, just 1 minute. So, one general announcement to all of you. Please
Yeah.
with the just revision session of the concepts from week 5 to 8. Please do not ask any general doubts or any AQ, PA or graded questions that we will cover in our sessions. So today's is just about revisions of week 5 to week 8 content, okay, which will be helpful for your quiz to exam. So I hope this is clear to everyone. Please maintain the decorum of the class. Thank you.
Thank you, Prashant. Okay, can I start?
Yes, ma'am, we can.
It's 8 o'clock. Can I start, Prashant?
Yes, ma'am, we can start.
Okay. Yeah, good evening, everyone. I am Usha Mohan, and I guess all of you know that I'm the instructor of the Statistics for Data Science 1. Because there is some problem with my web connection, I'm just going to switch off my video. I hope that is okay, Prashant.
Yes, ma'am, that's all right.
Yeah.
No problem.
Okay,
Yes,
I
ma'am.
will switch it on later. But as Prashant mentioned, there are certain rules that we want to follow. Is my screen visible, Prashant?
Yes, ma'am.
Yeah. Okay, the rules is this is again, as Prashant informed, this is a revision session. So at the end of every topic, I'll wait for a couple of minutes and I will take questions on those topics at the end of the because it is limited for 2 hours, I would request all of you to please not interrupt it unless it's a very serious matter. And the other thing is I want to inform is if there are any questions, you can use the chat box to write your questions and we'll take it up as and when I see the questions. Is that okay with all? Yeah? Okay. So
Yes, ma'am.
With this understanding, I'm just going to start this revision session. So these are the topics that we are planning to cover today. It will start with basic principles of counting and go up to conditional probability and Bayes theorem. And then after this, we are also going to introduce the notion of probability trees. Now, when we go to the basic principles, yeah.
Sorry to interrupt, ma'am, but I joined late. So what will you discuss today in this session, basically?
I just showed the list of topics that I'm going to discuss. Okay. I just showed the list of topics that I'm going to discuss. You can see it on the screen that I'm going to start with basic principles of counting and will go up to conditional probability and Bayes theorem.
Okay, ma'am. Thank you.
Okay. So we start with the discussion and I again request all of you to please use the chat box. We will stop by every, say, 10 minutes and we'll have a look at all the chats that you have typed in so that we can address every query. Okay. So the first, why do we need basic principle of counting? We need basic principle of counting because permutation and combination, in a sense, are principles of counting. We need to count how many ways of doing things. Again, why are we interested in permutation and combination? The idea is when I am talking about computing what is the chance of something happening, I am involving counting in some way. So to get hold of the chance of something happening, I need to understand permutations and combinations. And to understand permutations and combinations, I need to know what is the basic principles of counting. That is the reason why we start with the basic principle of counting. When we look at basic principle of counting, there are two basic principles of counting. And I again say basic principle because this is the foundation level. The two basic principles of counting are addition rule of counting and the multiplication rule of counting. As always, addition, whenever we talk about addition, it is always referring to the total number of ways A or B occurs. I think what we need to always understand is this A or B. So it is the total number of ways that two actions can occur. For example, you can choose a particular team. Now, because IPL is going to come very soon, if I'm choosing team A in say 5 ways and team B in say 6 ways, okay, then a total number of ways of team A or team B can be chosen as 11 ways. So that is what we say by N1 plus N2. On the other hand, when we talk about multiplication rule of counting, if A can occur in N1 ways and B can occur in N2 ways, the total number of ways A and B together can occur as N1 into N2. As in everything, I can extend this to multiple actions to extend it to N1 plus N2 plus NR. And this is N1 into N2 into NR. So these are the number of possibilities of doing all the R actions together. This is and action 1 and action 2 and action 3 up to action R. So the key difference that we need to notice is whenever I talk about and, it is the multiplication rule. Whenever I talk about or, it is an addition rule. So let's look at an example. Suppose I have 3 shirts and 2 pants. If I have to choose a shirt or a pant, there are 3 ways to choose a shirt. There are 2 ways to choose a pant. The total number of ways I can choose is 3 plus 2, which is 5 ways. I can choose either an orange, yellow shirt or a orange shirt or a green shirt or a black pant or a blue pant. On the other way, if I have to choose a shirt and a pant, if I choose an yellow, I can choose either a black or a blue to go with it. So with every thing, I have 2 more choices. So it is 3 into 2, which is 6 ways. That is 1. This is 2. This is the 3rd way. This is the 4th way. This is the 5th way. And this is the 6th way. This is an illustration of both the addition and multiplication rule of counting. So I'll just pause for any questions for a minute. If there are any questions, please use the chat box. If there are any questions, please use the chat box. I'll pause for a minute, otherwise I'll continue. So with an understanding of the basic principles of counting, we go ahead and introduce a very, very important notion that would be continuously used in permutations and combination, which is the notion of factorial. The notion of factorial is an extension of the multiplication rule of counting, which is nothing but the product of the first n positive integers, which I can write as n into n minus 1 into n minus 2 up to 1. So if there are n ways of doing first thing and n minus way of filling up the second blank and so forth, if I have n blanks to be filled with n objects, then I can see that there are n factorial ways of filling up these n blanks. By convention, 0 factorial is equal to 1. So now we go and introduce what is a permutation. A permutation, it is very important for us to understand a permutation is an ordered arrangement of n objects. I repeat, a permutation is an ordered. We always need to understand and remember this whenever there is an order or an ordered arrangement and an arrangement, it is called a permutation. So when we talk about permutation, there are again multiple things that we have looked at. First is when objects are distinct and repetitions are not allowed. The second is when objects are distinct and repetitions are allowed. Third is when objects are not distinct, and then circular permutation. We'll revise each one of them in detail now. When objects are distinct, for example, if I have 5 people, they are distinct, and I'm not allowing repetition, then the number of possible permutation of R objects from a collection of n distinct objects is given by NPR. So suppose I say, how do I pick up 3 people from 5 people to hold, or how to have first, second, and third position? I know that there is an order. I know I need to have first position, second position, third position. There is an arrangement. So It is definitely A, B, C here is different from B, A, C. There is an order that comes and that matters. Hence, we are saying that when there is an order, the number of ways or possible permutation of R objects, here R is 3 and N is 5, and the number of permutations is given by this formula, which is N factorial by N minus R factorial. Now, where do you find problems of this kind? So whenever they ask you questions of this kind, that, okay, from how many ways can you choose 3 people to fill up positions of president, vice president, or secretary? In which order is important and order is not important? I would suggest that you all look at the question very carefully, see if there is an order or an arrangement which is reflected in the question, and then apply the formula very carefully. One common confusion is students always confuse as to whether the question is a permutation or a combination. So we will address those issues after we introduce or revise what are the concepts of permutation and combination. So when repetitions are not allowed, then the number, this is the basic permutation formula. Objects are distinct and repetitions are not allowed. On the other hand, if I allow repetitions, then I can see that, and here you can see that the problem is, the type of problems that you will come here is, suppose I have 4 blanks and I'm saying, okay, you fill up or create a passcode. So I can fill up a passcode. If it is only numerals, then I can have any one between 0 to 9 here. I have 10 ways of filling up this, 10 ways of filling up this, 10 ways of filling up this, 10 ways of filling up this. So it's 10 into 10 into 10 into 10. On the other hand, if I do not allow repetition, if 0 can take the first position, I have 10 ways of filling this up. I'm not allowing repeating numbers, 9 ways of filling this up. I have 8 ways of filling this up and 7 ways of filling it up to give 10 into 9 into 8 into 7, which I can see it can be written as 10p4 or 10 factorial by 4 factorial into 6 factorial. So you can see that given the context of the problem, the objects are distinct. Here, what are the objects that are distinct? 0, 1, 2, up to 9 are distinct. Similarly, if it is an only alphabet code, I have 26 alphabets to choose from. So I can fill up this way, this first one in 26 ways. If repetition is not allowed, second in 25, third in 24, fourth in 23 ways. So it is 26 into 24 into 25 into 24 into 23. If repetition is allowed, this would be 26 ways. This is 26 way. This is 26 way. This is 26 way, which is 26 to the power of 4. And hence that the n to the power of r is coming from that. So again, depending on what is the context of the problem, you apply the formula either NPR if repetition is not allowed, or N choose R if repetition is allowed. Remember, the objects have to be distinct. Here I had 0, 1, 2, 9, which are distinct. Here I have A, B, C up to Z, which are distinct. So these are the first two important formula. The third thing is what happens when objects are not distinct. You would have seen problems of this kind where we have asked that, okay, how many different ways can we form 4-letter words using statistics? Here you can see that this S is appearing 3 times, T is appearing 2 times, I is appearing 2 times, A once and C once. So the number of objects here are not distinct. So in this case, you have a couple of formula. So the first one is the number of objects of n objects when p of them are of one kind. So in this, suppose I'm looking at data, I have A is of one kind and D and T of another kind. This is when you have problems of statistics. So you can see that n is totally 10. I have T, which is 3, S, which is 3. Then I have P3 is 1, P5 is 1, P4 is 2, where P4 is I. And the total number of ways of arranging this would be n factorial by p1 factorial, p2 factorial, pk factorial. So this is about the what we say linear permutations. In linear permutations, there are three key things that you need to remember. The first is when objects are distinct, repetitions allowed. The second is when objects are distinct, repetitions not allowed. And the final thing is when objects are not distinct. I pause it for a couple of minutes. If there are any questions, please ask me or write it in the chat. Any questions and clarifications regarding linear permutation?
No,
Can I
ma'am.
proceed?
Yes,
Okay,
ma'am.
right. Thank you. So once we know about the linear permutation, the next thing that we need to understand is the circular permutation. We already have established in a linear permutation, if I have n objects, then the way I can arrange these n objects among themselves is n factorial. This is what we have already. So suppose I have A, B, C. I can arrange it as A, B, C, A, C, B. I can arrange it as BAC, BCA, CAB, CBA. So it is 3 factorial, which is 6. I have 1, 2, 3, 4, 5, 6, 6 ways of arranging it. Now the circular permutation, again, there are two things, two ways to look at it. One is the clockwise arrangement and the anti-clockwise arrangement are different. To obtain the circular permutation, what we did do is you fix any one of the permutation objects. For example, if I fix A, then the remaining ones, that is B, C, D, I can view as linear permutation. If the clockwise and anti-clockwise are different, I know that this BCD, CDB, these are the linear permutations of BCD, and that can be done in n factorial ways, that is 3 factorial ways. This 3 is n minus 1 factorial. I repeat, to get the circular permutation, you fix one of the objects and then you look at the linear permutation of the remaining. The remaining can be arranged among themselves. So the remaining, I'll have n minus 1. If I fix one of it, if I have n objects and fix one of it, I have n minus 1 objects. That n minus 1 object among themselves can be arranged in n minus 1 factorial way. So the number of ways n distinct object can be arranged in a circle is equal to n minus 1 factorial. Remember, in this case, the clockwise and anti-clockwise are different. So the problems of this kind is in how many ways can people sit in a round table? How many ways can a garland be actually arranged? How many ways can I come up with people who are actually sitting around in a circle? And problems of this kind, you from the context of the problem, you decide whether the clockwise and anti-clockwise are different. If it is generally people, the clockwise and anti-clockwise are different. But when you are coming off, say, for example, a garland of red stones or garland of black beads and red beads together, there the order, typically the clockwise and the anti-clockwise are same. So if the clockwise and anti-clockwise are same, the number of arrangements is n minus 1 factorial by 2. So any questions with the permutation part? So to just summarize the permutation part, if objects are not distinct but repetition is allowed. Can you give me an example of it, Saravanan? What do you mean by objects are not distinct and a repetition is allowed? I think the question of statistics is the same, right? If objects are not distinct and repetition is allowed, I didn't get your question. If you can give me an example of your problem, I will be able to address it.
Ma'am, let's say, for example, if there's a word called data, and then they're asking us if the A is not distinct, ma'am, and then they're telling that repetition is allowed, and we're asked from 4-letter word. So for that, is
Yes.
it like that?
But when you are using data, the way you would see is the objects are agreed.
Ma'am.
See, when I'm looking at data, okay, what do I have in data? I have DATA. One way I can see it is I can write this as A1 and A2. Now I have 4 distinct objects. Do you agree with me?
Yes, ma'am.
Right. Now, how many ways can I arrange these 4 distinct objects?
4 power 4 ways.
4 factorial ways?
Yes,
But
ma'am.
now the A1 and A2 are same. How many ways can I arrange A1 and A2 among themselves?
3
2.
factorial.
2 ways, which is 2 factorial. Agreed?
Oh, okay.
Right. So I need to discount that. That is why I have n factorial by p factorial. That is how we have got that, n factorial by p factorial. Is that clear?
Okay.
Now suppose I have an A1, A2, C1, C2. Then I can, this is 6 factorial ways divided by 2 factorial, 2 factorial. Is that clear?
Yes, ma'am.
The same logic I'm going to extend it.
Ma'am, if we take 5 blue balls and we have to arrange it, then like
Yeah,
how
5.
5 blue balls, so they are all equal, not
Yeah. So there's only one way of doing it, right? 5 blue balls, all of them are same. Okay. So there's only one way of doing it.
Okay.
Agreed?
It's mean n is equal to p.
See, what? Yeah, n is equal to p there, right? So
Okay,
n
okay.
factorial, because how many are of the same kind? One kind, right? N is equal to p. So what is n factorial by n factorial?
1.
But
1.
here,
So there's
ma'am,
only one way, right? Pardon?
all alphabet or anything, all are same. Then I can say n is equal to p because n
Yeah, that's what
factorial.
I'm saying. So there is only one way of arranging 5 blue balls,
Oh, okay. Thank you.
right? Only one way of arranging 5 blue balls. Because they are all of the same kind, right?
Yes, ma'am. Yes.
Yeah?
Yeah, got it.
Would you
Ma'am,
agree? Yeah.
in the same, let us take the statistics example. How many words can be formed with all the letters given in the statistics word? But all the words should start with A. Something like if it is conditional, how to solve this?
Okay, the word should start with A, right?
Yeah, that is
How
what.
many do you, okay. Now I need to start by looking at how many 3 letter, how many 4 letter, how many 5 letters. That is the way I need to look at it. Is that right?
Okay. Okay, ma'am.
Yeah.
So now this
Yeah.
the total number of permutation will contain all the letters starting from 2 letter to 10 letter. Does
Yeah,
it mean that?
whatever it is. Yeah. So that's, see, again, you need to, typically in an exam, you'll not be asked about words with meaning because that is very contentious. Okay. So for example, I can follow an ACST. It might not mean any meaning, but I know
Oh,
that I can write this word, right?
yeah.
Is it
So
clear?
now,
So if I fix A, then I know the second thing can be filled with any one of the remaining TSCI.
Yes,
Okay,
yes,
4 ways, any 4 of the thing. Again, it depends on whether repetition is allowed or repetition is not allowed.
yes.
oh,
If repetition is
Agreed?
allowed, then I
If
can write
repetition is
every
allowed, each one of them is 4, 4, 4. 4
Yes.
factorial. If A is also allowed, it will be 5, 5, 5, 5. It all depends on the nature of the problem. Is it clear?
no,
Suppose if I'm allowing A, even that is repetition is allowed, right?
okay, ma'am.
You
Good
got
evening.
it?
No,
The
madam,
kind
good
of-
evening.
Yeah,
Madam,
please.
Good evening, madam. Madam, this in
Yeah.
case of circular permutation, clockwise and anti-clockwise and same and different, if you can make the distinction between these two in
See,
case of
for
the problems.
example, I have 4 people sitting, right?
Yes, madam.
4 people. What you see on, can you see on the screen?
Yes, madam.
There A, B, C, D are 4 people. How many ways can they be arranged in this one?
Circular.
In the table. Okay. So I can have either A, B, C, D or A, C, B, D. This is so here you see A, B, C, D and A, B, C, D. These are actually same in some order. Do you see that?
Yes, madam. Okay.
The clockwise and anti-clockwise are the same, but they are different circular permutations. Because is that clear?
Madam, only the
If you look at this, to the right of A is B is A. Here to the right of B is this one left of. So between, in a sense that you can see that these are different permutations in the way the clockwise and anti-clockwise are not the same. Is that clear?
Okay, madam. Okay. Yes, madam. Okay.
Yeah.
Yes, madam.
But
Clear.
however, suppose this was a red bead, black bead, red bead, black bead. Okay. The
Yes, madam.
clockwise and anti-clockwise do not matter. So it depends on the context of the problem, whether you know that the clockwise and anti-clockwise are same or anti-clockwise and anti-clockwise are not same. That is what we are trying to say. Is that clear?
Yes, madam.
Yeah.
Yes, yes.
Any other questions on permutation?
Yes, ma'am. In linear permutations, ma'am.
Yeah.
We're talking about
Pardon?
the stat in linear permutation.
Yeah.
Yeah. So we were talking about
What
the
in
word,
linear permutation?
yeah. So we were talking about the word statistics. So
Yes.
the condition where we can have all the t's coming together. How will we solve that problem?
Can you please repeat your question?
I mean, in the word
See,
static.
I just want to be very clear that this. So, what is the question? I go back to statistics. Yeah, here, what is the question that you want?
Yeah. So the question is, let's suppose we have to find out the number of permutation where all the t's come together.
So, if all the t's come together, right? I
Yeah.
will consider these 3 t's as one alphabet. It's all right.
Okay.
Okay.
And
So,
we will
apart
not.
from that, so I now will have, instead of 10, I'll have an STISICS. So
Okay.
I'll have 1, 2, 3, 4, 5, 6, 7 ways of doing it. Okay. Of which I know that I have 3 S's, 2 I's, 1 T. Okay, I have an A also, right?
Yeah.
1 A and 1 C. Now, the same question, if you want to look, this is how you will look at it. And between them, whether it's a T or a T1, T2, T3 or a T2, T1, T3, it doesn't make any sense because there's only one way of doing it, right? Because the T's are the same. Agreed? So I can consider all these 3 T's as one block and I can get the formula, apply the formula. Is that clear?
So that would be factorial 8 upon factorial 3 into factorial 2, right?
Yes, into factorial 2 because I have 2 I's and 3 S's.
Okay.
Is that clear?
Yeah, clear.
See, but however, if you were applying the people are together, those people are distinct. Okay, so this are not distinct will not apply there because people are distinct and you need to see how many ways those people among themselves can be arranged. For example, I have A, B, C are the 3 people. Among them, I have 6 factorial ways of their being arranged. Is it clear?
Oh, okay. So if they are not distinct,
You need
in
to
that case,
understand whether they are distinct or not distinct. That is something that you need to understand. Okay?
okay.
Ma'am,
Right? Yeah. Please go
in
ahead.
this problem, the 50,400 ways, we are arranging all the we are arranging the 10 letters. In the 10 letter, all the 10 letters, I mean 50,400 will be 10 letter words only, no, madam?
Yes, all the way. That's what I'm permuting all the 10 objects. I'm not choosing anything out of them.
Okay.
Yeah, all the 10. But for example, in the statistics, SSTA, okay, SSTT, ICSI is same as that. Suppose this one S1, S2, X2, X1, TA, ICSI. That's what I'm trying to say.
Yeah,
These two are same. That's why you're dividing it by the, see, for example, when we looked at the data question, right? Because statistics is too long a word, I'll use this data. Okay. When I see data and I look at DA1, TA1, okay? Or let me look at just D, A1, or just let me look at C1, A1 or ACA, A1, A2, A1, C1, A2. Okay. How many ways this can be arranged? I can have an A1, C1, A2,
Three
A1,
factorial.
C2, A1, C1, A1, A2, C1, A2, A1,
6 ways.
A2, C1, A1, A2, A1, C1. Right? These are the ways I can arrange.
Yes, ma'am.
Would you agree?
Yeah, yeah.
But these two are same.
So we are reducing
And
we
these four are also same. Yeah. So the total number of ways is only 2, right?
Oh,
Ma'am, how could these two are same? C A1, A2 and C A2, A1.
Because A1, see, because finally A1 and A2 are same, right? They're not distinct. If I put a blue ball, a red ball, and a blue ball, red ball, they are the same, right?
Okay,
so
ma'am,
it's
got it.
I'm just calling this red ball 1, red ball 2, red ball 2, red ball 1. Are they different
No, ma'am.
permutations,
No.
arrangements?
No.
That's what I'm trying to say. Is it clear?
Yeah.
That's why you're
Yes,
dividing it.
ma'am. Clear. So,
Is it clear? That's why we
yes,
are
ma'am.
dividing it. Whether I'm putting second red ball first and the first red ball next doesn't make a difference. Is that clear?
yes, ma'am.
Okay. So if there are no more questions in permutation, we'll go and introduce combinations.
And just one
Can we
more
go?
question.
Yeah.
Just one more
Yes,
question.
please.
So we're taking the case of the persons. Like let's suppose we have 8 people and we want arrangement of seating of the 8 people. The normal way of doing it is factorial 8, right?
Yeah.
Now we want 3 of
Arranging
them.
8 people together. Yeah, it is factorial 8. Yeah.
Yeah. Now we have a condition that we want 3 people to sit together. In that case, we will have 7 factorial into 3 factorial. Is that correct?
Yes, exactly. Yeah.
Okay. Now I got it.
Okay. Right.
Yeah, I got
Okay.
it.
Because you're treating that 3 people as a single block. Within
Yeah,
the block, they can be arranged in 6 ways. Okay.
yeah. Thank you, ma'am.
Right. Okay. So the next thing is, see, always remember that when we talk about permutations, the order and the array, that is extremely important. Okay. But a good example is, suppose from a class of 40, I am choosing 3 people. I'll give you 2 conditions. One is, from a class of 40, I'm choosing 3 people to be president, vice president, and secretary. Okay. The second thing is, from a class of 40, I'm choosing 3 people to represent the students' council in the university. Okay. What is the difference between what is said first and what is said second?
In first, order is important. In second, order is not
Second
important.
order is not important. In the first, whether the first person, suppose I'm choosing A, B, C, A being president, B being vice president, and C being secretary, is different from BAC, where B is president, A is vice president, and C is secretary. Would you all agree with me?
Yes, yes.
But in the second case, when I choose ABC, whether I'm choosing ABC or BAC, it is the same, because both of them are 3 people without any order among them, who are representing the class in the student council, overall student council. I'm not assigning any order between A, B, and C. Is the distinction clear?
Yes, yes.
Yeah. So this, the first case where the order is important, is what we always term as a permutation. And in the second case, where the order is not important, is what we call a combination. Okay. So the number of possible combination of, again, n distinct objects, R objects. The permutation was NPR for every, so, but n choose R. Okay. I know that this is NPR. So this NPR is nothing but R factorial into n choose R, or n choose R is n factorial by R factorial into n minus R factorial. The reason is these 3 combinations, A, B, C, B, A, C. Okay. And so here, when I had, suppose I have ABC and I'm choosing AB, AC, BA, BC, CA, CB. Okay. Now CA, CB same as BA, BC. AC, CA same as AC, same as CA. AB is same as BA. Would you agree with me? Yeah.
Yes,
So how many ways can I order? If order is important, how many ways can I choose 2 people from 3 people? It is 3P2. Agreed?
Yes, ma'am.
Yes, ma'am.
How many ways can I choose? It is just 3C2. But what is the relation between number of permutation for every combination? So every permutation among themselves, these R people can be ordered in R factorial ways. So I have N factorial, that is NPR into R divided by R factorial is N choose R. And that's why I have this NCR is N factorial R factorial into N minus R factorial. So that is the relation between a combination and a permutation. Now, one of the useful results is the number of ways. Suppose I have 5 objects. Okay. How many ways can I choose 3 objects from 5 objects? It is 5 choose 3. Would you all agree with me?
Yes, ma'am.
Now, choosing 3 objects from 5 is same as not choosing 2 objects from 5. Would you
Yes,
all
ma'am.
agree?
Yes, ma'am.
Yes or no? How
Yes,
many
ma'am.
ways can I not choose 2 objects from P? That is 5 choose 2, right? So you can see that N choose R is same as N choose N minus R, because the number of ways of choosing R from N is same as not choosing N minus R from N. Would you all agree with me?
Yes, ma'am.
Okay. So the N choose N by this one is equal to 1 and N choose 0 equal to 1. Now let's look at this important combinatorial identity. What is N choose R? This is choosing R from N. Is that clear?
Mm-hmm.
N choose R. N choose R is choosing R from N. Okay. Let me fix some object. Okay. Now this, out of this N objects, let me choose any one object. Let me call that object some star. Okay. Now in this N choose R, there are 2 ways. This star is included or the star is not included. Would you all agree with me?
Mm-hmm.
Suppose the star is a part of this N objects, the star could be either included or the star could not be included. Right? Do you all agree? Suppose I have to choose 3 people from a class of 5 people. I can do it in 5 choose 3 ways. Agreed?
Yes, ma'am.
So suppose Rajesh is one of these 5 people. In this 5 choose 3, Rajesh is either there or Rajesh is not there. Would you all agree?
Okay.
Now, if Rajesh is there, that is among the chosen 5 choose 3, how many more should I choose? I've already chosen Rajesh. How many more should I choose?
2.
2. And how these 2 from how many can I choose those 2? How many more are left to be chosen these 2 from?
Only 2 are left.
4 are from 4, right? Because Rajesh is one of these 5. Agreed? So
Yes,
how many ways can I choose 2 out of that 4 people? That is 4 choose 2 ways. Would you all agree?
Yes, ma'am.
Now, if Rajesh is not there, how many people I should choose? I should choose 3 because Rajesh is not there, right? I should continue and choose these 3 people from these 5 people. Is that clear?
Yes, ma'am.
See, one Rajesh is there, another Rajesh is not there. The person who has been chosen is either Rajesh or not Rajesh. If Rajesh is chosen, I have to choose how many? 2 more from 4. Is that clear?
Yes, ma'am.
If Rajesh is not there, okay, the person who I have chosen is not Rajesh. How many are left? I've already chosen one person. So how many do I have to choose? More. See, either Rajesh is there or Rajesh is not there, right? Agreed?
Mm.
So I have to choose these 3 people from the remaining 4. If Rajesh is already there, the number of ways I can choose the remaining 2 from is 4 choose 2. Agreed? If Rajesh is not there, I'll have to choose another 3 from the 4, and that can be done in 4 choose 3 ways. So in typically 5 choose 3 is same as 4 choose 2 plus 4 choose 3. That is what this means. Is that clear? So
Yes,
I'm
ma'am.
fixing an object. If that object is there, then afterwards it is n minus 1 choose r minus 1. If that object is not there, I need to choose this r from n minus 1. I'm fixing one object. From the remaining n minus 1, I either choose r minus 1 or I choose r. So that is how we get this identity. Okay. I'll just allow you to
How
think
are
about
we
this.
fixing that object if Rajesh is not there?
See, forget about that. See, this n choose r is there, right? What does this mean? From n objects, you choose r objects, right? That is what it means. Okay. Now I am fixing one. I'm taking one object. I've chosen one object. Okay. So how many do I have remaining to choose?
4
N
n
minus
plus
1.
1.
If I n
4.
minus 1. Agreed?
Hmm.
Is that clear?
Yes, ma'am. Yes.
If I'm choosing one object, I have only, because I've removed that one object, right? Now, there are 2 ways. Either this object which I have chosen is included or it is not included. If that object is included, okay, then I only have to choose r minus 1 from this n minus 1 because this r is already included in the r objects. Is that clear?
Yeah.
Now, if this r is not included, I have to choose this r from the n minus 1. I'm just fixing one object. Okay. I think this explanation is already given. You can go through that explanation in the notes, but this is an important combinatorial identity. In the interest of time, I'm just going to go ahead. If there is a problem, I'd request Prashant to take it up in a tutorial. Okay. But the only thing I wanted you all to tell is this is an important combinatorial identity. Now, one thing which you repeatedly see in exams is when do I use permutation and when do I use combination? So always remember when the order matters, okay, use permutation. When the order does not matter, use combination. So let's look at it. A password consists of 7 characters, order matters. How many different passwords are possible? Would you use a permutation or a combination?
Permutation.
Permutation. Very good. Okay. A pizza parlor offers to build your own pizza. Choice of 5 different toppings from a list of 10 toppings. Would you use a permutation or combination?
Combination.
Because it doesn't matter whether you put the order does not matter. Is that clear? Forming a 4-digit PIN code, permutation or combination?
Permutation.
Order matters. Order matters, right? A bookshelf has 8 different books. I want to arrange 5 books. How many ways can these 5 books be arranged? It's books. Remember, it is books.
Permutation.
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 If I want to choose 5 books, then
It is combination.
it is combination. Okay, so these look very simple, but nevertheless, you need to always understand from the context of the problem whether you're having a permutation or a combination. Okay. Now, for example, this is again very common problems is suppose team member roles and positions are distinct, then order of selection matters, you'd use permutation. For example, in how many ways can a committee of 4 members be selected from a group of 10 people? Would you use a permutation or a combination?
Combination.
Pardon? Combination, because I'm selecting 4 members. But in how many ways can a committee of 4 members be selected to hold specific positions?
Permutation.
Permutation. Forming a 4-letter code using A, B, C, D. Every letter can be used only one. Against it is permutation. Each letter can be used. It is a permutation. Okay. So what we have learned so far is what is a permutation, what is a combination, examples from the context of the problem. You decide whether you want to have a permutation or combination. When we look at permutation, you need to understand whether they are distinct objects with repetition or without repetition, or whether it is a circular permutation. This is important. Okay. Can I go forward? Any questions? Let's pause for a couple of minutes and go to the probability because I think we are running out of time. Can I go to the probability review?
Yes,
Yes,
ma'am.
yes,
madam.
Yes, ma'am.
Yes, ma'am.
Okay. So the first thing that we need to understand when we are talking about probability is, first of all, why are we learning probability? The reason why we are learning probability is, see, we are always encountering uncertainty in our life. Okay, nothing is certain. Always we hear people telling that I will come between 8:45 and 9 o'clock, or things would start. That is how we are not telling that I am coming exactly at 9:20. There is some uncertainty there. So whenever there is an element of uncertainty, probability helps us model situations which are uncertain in nature. That's why we need to understand probability. So we need to build this theory of probability, and the building blocks of this probability starts with what is called a random experiment. A random experiment is an experiment whose outcome is not predictable with certainty. For example, when I toss a coin, I know it would be a head or a tail, but can I be sure that it would be a head?
No, ma'am. No.
No, right? I know the outcomes. One of the common mistakes people tend to do is they say that a random experiment is an experiment with unknown outcomes. That is incorrect. A random experiment, it's an experiment where the outcome is not predictable with, I know the outcome. I know the outcome is either a head or a tail, but I do not know whether the outcome would be a head or a tail. Is this distinction clear? For example, when I roll a die also, I know I'll get either a 1, 2, 3, 4, 5, and 6. But whether I'll get exactly a 1, 2, I do not know the outcome. I cannot predict the outcome with certainty. That's why it is called a random experiment. Is this clear?
Yes, ma'am.
Right? So this random experiment, a collection of all basic outcomes, is what we call a sample space. This is the second building block. It is all basic outcomes. Now, for example, I'm going to motivate this entire thing with tossing a 2 coins. For other examples, you can refer to the lectures. If I toss a coin twice or toss 2 coins, I know the outcomes of the experiment are head in both tosses, head in the first toss, tail in the second toss, tail in the first toss, head in the second toss, or tail in both tosses. This is what I refer to as the sample space of the experiment. When I roll a die once, it is just 1, 2, 3, 4, 5, or 6. These are the all possible outcomes. When I roll a die twice, I know I could have 1, 1, 1, 1, 2, up to 1, 6. There are 36 possible outcomes, and all of them is what I constitute the sample space. Now, an event is a subset of the sample space. For example, if I am defining the event that head appears in the first toss, that event even is HH and HT. Head in the second toss is HH, TH. Both the outcomes are the same. It is HH, TT. So I can define events as subsets of the sample space. Now, once I define events, I recognize that the sample space can be viewed as the universal set, and these events are subsets of the universal set. So when I talk about subsets, all what I learned in set algebra would work here. So I can talk about union of events. I can talk about intersection of events. I can talk about complement of events. Okay. So what is the sample space here? Tossing 2 coins. We have just found that here. Sample space is HH, HT, TH, and TT. You can write with me. Head in the first toss is HH, HT. This is HTH. Head in the second toss is TH, HH, TH. Head on the first or second toss. What is the sample space here? It's either in the first toss or the second toss. Okay. Head on the first and the second toss is HH. Is this clear? So these are my events, and you can see that the fourth event is nothing but the union of the second and third event, and the fifth event is the intersection of the second and third event. Is the notion of sample space, events, and the set operations on the events clear?
Yes.
Yes, ma'am.
Okay. So once we know what are events, there are two important events. One is called the null event, and it is represented typically by phi. And then afterwards, we call two events which cannot simultaneously occur as mutually exclusive event. That is, the occurrence of one event prohibits or does not allow the other event to happen. For example, can head and tail appear at the same time?
No. No, ma'am.
Head and. So those two are mutually exclusive. Similarly, a complement of an event, if head occurs, the complement is tail. What is the complement of event even here?
Odd numbers.
What is the complement of event even here?
TH and TT.
TH and TT. Or how would you describe that?
Tails in the first toss.
Tails in the first toss. Okay. So we know that we can define the complement of an event. And the example again, outcome is tail. You can see that head on the first toss and tail on the first toss, the event complement. Okay. So this is how I'm just going to skip this Venn diagram part. But what is more important, and we are going to spend the next hour here, is to now introduce formally probability of events. When we talk about probability axioms, I think in the lectures I talked about the empirical and the all the other ways of having probabilities. But here I'm going to just focus on the axiomatic approach, where there are three important properties. The first property says that the probability of any event is a number between 0 and 1. The second axiom says the probability of sample space is 1. In other words, it means that the outcome of the experiment is definitely at least one outcome is going to definitely happen. So the probability of the sample space is 1. The third axiom talks about the probability of the countable union of events, which is equal to the sum of the probability of events. Yes, Rekha? Rekha, you have raised your hand.
I'm so sorry, ma'am. By mistake, I raised
Okay,
my hand.
right. Okay, right. So these three axioms are used to get hold of a lot of rules, and one of the rule is what is called the addition rule in probability. Now, the third axiom is actually the probability of countable union. I can apply that to a finite union also. That probability of union I going from 1 to k ei is summation I going from 1 to k probability of ei. This is the probability of finite union is sum of probabilities. Now, when you are talking about a finite union, if even and E2 are disjoint, probability of even union E2 is sum of the probabilities. But what the addition rule tells us is the following. When I have events which are not necessarily disjoint, so suppose I have even and E2, and I have an even intersection E2 here, I know that I can look at this as 1. This is 1. This shaded area is 2. This is 3. So probability of even union E2 is nothing but probability of 1 plus probability of 2 plus probability of 3. This is from my rule or axiom of probability. Would you all agree with me? Yeah?
Yes, ma'am.
Yes,
But
ma'am.
what is probability of 1? Probability of 1 I can write as probability of E1 minus probability of E1 intersection E2. Probability of 2 is nothing but probability of E1 intersection E2. Probability of 3 is probability of E2 minus probability of E1 intersection E2. To give me that, probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2. And this is called the addition rule of probability. Remember, whenever I talk about union, I'm talking about E1 or E2. So the addition rule of probability states that the probability of event E1 or E2 occurring is probability of E1 plus probability of E2 minus the probability of intersection. So let's apply the probability or addition rule to this problem. A customer goes into a clothing store and purchases a shirt with probability 0.3, a pant with probability 0.2, and will purchase both a shirt and pant with probability 0.1. Let's identify the events. What are the events here? S is the event of customer purchasing a shirt. What is the probability of S?
0.3.
What is the probability of P, which is the probability of purchasing a pant?
0.2.
0.2. Okay. Now we are interested in knowing what is the proportion of customers who purchase neither a shirt nor a pant. So what is the, describe the event the customer purchases a shirt or a pant. What is that event? Purchase a shirt or a pant.
0.5.
Union.
Yes, union P, right? Purchases a shirt and a pant.
Intersection.
S intersection P. Okay. Now, do I know what is S intersection P?
Yes.
Purchasing both a shirt and a pant. What is the probability of S intersection P?
0.1.
0.1. What is the probability of purchasing a shirt or a pant? From my addition rule, I know that is a 0.3
0.4.
plus 0.2 minus 0.1. Is that right? Which is a 0.4.
Yes.
Till here, is it clear?
Yes, ma'am.
Now I want, so again, how would I tell what is a complement? How would I describe S union P complement? S union P is either a shirt or a pant, right? What is S union P complement? Describe it.
1 minus P of S union
I'm not
P.
asking for the value. I'm asking you to describe it. S union P is either a shirt or a pant. What is S union P complement?
When he does not buy anything.
Neither a shirt or a pant. Is that clear? So that is the most important thing, is always describe even before you apply. Okay. So you can see that I am interested in knowing what is S union P complement for neither a shirt nor a pant. And I know that that complement is 1 minus probability of S union P, which we have just found out. For this, so I have 1 minus S union P complement of S union P is 0.6. Is this clear? So whenever you're presented with the problem, identify the events, okay? And then whatever question is there, you translate that question into the event. So this is neither, I know either, I know the neither has come here. I've used complement rule, I've used addition rule to come up with the probability. Any questions here, please?
No.
Okay. Now, one of the most important things is when I have a random experiment for which the outcomes in the sample space are equally likely to happen. And experiments of this kind is when I'm rolling a die, I know that 1, 2, 3, 4, 5, 6 are all equally likely to happen. When I'm tossing a coin, I know if it's a fair coin or an unbiased coin, head or tail can be equally likely to happen. In that case, I know that the probability of one happening is 1 by 6. So number of outcomes divided by the total number of outcomes. That is what I have. Okay. For example, again, you can see on your screen, I'm rolling a fair dice. The sample space is 1, 2, 3, 4, 5, 6. I'm defining A to be the event that the outcome is 1, 3, and 5. What is the probability of A?
3 by 6.
It's 3 by 6, which is the same as 1 by 6 plus 3 by 6 plus 5 by 6, which is 3 by 6. Okay. What is the probability of B? Outcome is greater than 4. Strictly greater than 4.
2 by 6.
2 by 6.
2 by
2 by
6.
6.
2 by 6.
Now, C is the event that the outcome is either odd or greater than 4. So, what first tell what is C in terms of A and B. What is C in terms of A and B?
Either or greater than 4.
Yeah. So,
Union
what
of
is
A.
the? It is A union B.
Yes.
1 by 2 plus 2 by 6.
Plus 2 by 6. But what is probability of A union B? From my addition rule, it's probability of A plus probability of B minus probability of A intersection B. What is A intersection B here? First, describe the event.
A intersection B is 0 here.
It's 5.
No,
5.
5, right? I
Oh,
need the
yes,
outcome to be odd and greater than 4.
ma'am.
5 is both odd and greater than 4, right?
Yes.
Yes, yes.
What is the probability of A intersection B?
1 by 6.
1 by 6.
1 by 6. So what is the probability of C, which is probability of A union B? It's going to be 3 by 6 plus 2 by 6 minus 1 by 6. Is that clear?
Yes.
Yes, ma'am.
Yeah, which is 4 by 6. Is this clear?
Yes, ma'am.
Okay, right? Okay. The next important notion, is this clear that where we have looked at probability axioms, the addition rule of probability, and how we apply the addition rule of probability? Any questions? I'll pause for a few minutes here. Any questions?
No, ma'am.
Can I proceed?
Yes, ma'am.
Yes, ma'am.
Okay. So the next important notion that we have is the notion of conditional probability. Again, see, suppose I am tossing a coin twice. I know that the outcomes are HH, HT, TH, and TT, right? Okay. Now I toss a coin and I observe that the first toss is a head. Okay. What is the chance? So in the first toss, so let me go and now I think it's a good time for me to introduce the probability tree thing. Okay. I toss a coin one. What are the outcomes of the toss? Head and tail. Can you see the tree structure here?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay. So I toss a coin once. I can either get a head or a tail. I toss a coin the second time. Okay. I know that when I toss a coin once, what is the chance of the head? It is 0.5. The chance of a tail is also 0.5. Till here, is it clear? Now, when I toss a coin twice, this is the first toss. This is the second toss. Agreed? Again, the second toss could be a head or a tail.
Mm-hmm.
Is it right? Now, what does this tell me? This is telling me it is a head. Both the first and the second toss are a head. So this is head, head. This is first toss is a head, second toss is a tail. This is head. First toss is a tail, second toss is a head. And a tail, tail. First toss is a head, tail, second toss is a tail. Till here, is it clear?
Yes.
Now I want to know, this is probability 0.5, this is probability 0.5. Second toss, what is the probability of head? It is again 0.5, second toss, right? This is also 0.5, this is 0.5, this is 0.5. Till here, is it clear?
Yes.
Right? So this is, till here it is clear. Now I'm asking, what is the chance that you have got a head in the second toss? What is the chance of you have got a head in the second toss, given that you had a head in the first toss? That is 0.5 only, right? I'm tossing a coin twice. What is the chance that the second toss will also be head, given that there was a head in the first toss?
0.5.
It is going to be the same. So what is the chance that the head is in the second toss, given that there was a tail in the first toss?
0.5.
0.5. Agreed. So without going into the calculation, I'm telling, when you're tossing a coin, does whatever come in the second toss depend on what was the outcome in the first toss?
No.
It is not dependent. Till here, is it clear? All of you agree with it?
Yes,
That the outcome of the second toss does not depend on whether I had a head or tail in the first toss, because I could get a head or tail in the second toss also. Till here, is it clear?
Yes.
Okay. Now let's look at the same structure. Okay. I'm having a bag of 4 white balls and 3 black balls. Okay. What is the chance with which I can get a black ball? I'm picking up only one ball.
3 by 7.
3 by 7. If I pick up a black ball, I'm going to go to a black bag 2 with 3 white balls and 6 black balls. Okay. But however, if I pick a white ball, I'm going to go to a bag which has 4 white balls and 5 black balls. Okay. Is this clear?
Can you repeat this?
See, if this is my bag 1. Okay. I'm picking up one ball. What are the 2 events that can happen? I can either pick up a black ball or a white ball.
Yes, ma'am.
The black ball I can pick up with a probability of 3 by 7.
Yes.
The white ball I can pick up with a probability of 4 by 7. Right?
Yes.
If I pick up a black ball, I'm going to a bag 2 which has 3 white and 6 black balls. Okay. If I pick up a white ball, okay, I'm going to a bag with 4 white and 5 black balls. Is that clear?
Okay.
Now again, I'm picking up another black. Again from here, I'm picking up a ball, one ball. What are the 2 possible outcomes?
Either a white ball or a black ball.
What is the chance of picking up a black ball here?
6 by 9.
6 by 9. What is the chance of picking a white ball here?
3 by 9.
3 by 9.
What is the chance of picking a black ball here?
5 by 9.
What is the chance of picking a black ball here, white ball here?
4 by 9.
4 by 9. Now, suppose this is black ball, black in the first draw, white in the first draw, black in the second draw, white in the second draw, black in the second draw, white in the second draw. What is the chance of picking up a black ball in the second draw, given you have picked up a black ball in the first draw? That is 6 by 9. Would you all agree?
Yeah.
What is the chance of picking a black ball in the second ball, given you have picked up a white ball in the first draw? That is 5 by 9.
Yes.
So getting a black ball in the second draw, does it depend on whether you had picked up a black or a white ball in the first draw?
No.
Or is it independent?
It's independent.
How is it independent? What is the chance of me finding a black ball in the second bag, given I had picked up a black ball in the first bag? That is 6 by 9, right?
Both the second bags are different in these
It
cases.
is different and the probabilities are different. So the chance of you finding a black ball in the second, are the chances the same? Is probability B2 given B1 same as probability B2 given W1?
No.
Here is the probability of head2 given head1 same as head2 given tail 1.
Yes, it was same.
Whereas here the events are not independent here. They are dependent on what was your first draw. Here it is independent of what was your first draw. Do you see that?
Yes, ma'am.
In this case, getting a head or a tail in the second toss is independent of what was the outcome in the first toss. Agreed?
Yes, ma'am.
Whereas here you can see that
Yes, ma'am.
there is a dependency. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right? So now let me ask you this question. Suppose I am rolling a die. These are the outcomes. 36 outcomes, right? I'm defining an event even which is sum of 7. Total sum of 7. What are the outcomes that will contribute to it? The sum of the outcomes is 7. What are the events that contribute to it? 1, 6.
Yeah.
5, 2,
5,
1,
4,
5,
3,
3,
4,
4,
4, 3,
4, 3,
3,
5, 2,
5, 2,
5, 2,
6, 1.
and
6,
6, 1.
1.
Agreed? Now let me put the
Yes.
same structure. The first thing is outcome on the first toss, which is 1, 2, 3, 4, 5, and 6. Okay, this is the outcome of the first toss. Outcome of the second toss is again, if it is a 1, I could get a 1, 2, 3, 4, 5, 6. Again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I can get a 7 irrespective of what was my first toss, right? I can get a value of sum of 7 irrespective of what was my first toss. Would you all agree with me?
Yes, ma'am.
No.
Yes, ma'am.
Yeah. If I get a 1, I can get a sum of 7 if I get a 6 in the second toss. If I get a 2 in the first toss, if I get a 5 in the second toss, I'll get a set of 7, right? So sum of 7 can happen irrespective of what was the outcome in the first toss. Would you all agree with me?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Now let me define E2 to be sum of 8. What are the outcomes that will give a sum of 8?
0.
2, 6,
No.
6,
2,
3,
6,
5,
3, 5,
3, 5,
4,
5,
4,
3, 4, 4,
6,
6,
2.
2.
6, 2.
The sum of 8, does it depend on what was your first toss?
No.
Yes, it does depend.
It does
It
depend.
does. It does.
Agreed. So this
Yes.
is the intuition behind talking about there are some events where they are independent of each other, like a head in the second toss is independent of whether your first toss was a head or a tail. A sum of 7 can happen irrespective of what was my first toss, but a sum of 8 cannot happen. Whereas here in this bag example, probability of picking up a black ball in my second draw depends on whether I had picked up a black or a white ball in my first draw. Till here, is it clear through the examples what is an independent and dependent thing?
I have a doubt
Yes,
in the
ma'am.
ball question, ma'am.
Mm-hmm.
The first,
Please go ahead.
the first bag has 4
Yeah.
white and 3 black. If
Yes.
a black ball is chosen, then the bag 2 will have 2 black and the same 4 white, right?
Yeah. See, I'm just saying you are going to another bag. You could also tell that, okay, I'm this one, I can have 4 black and 2. I'm choosing black, 2 black balls because I've chosen this black ball and I'm keeping it outside. In this case, this would be 3 white and 3 black.
3
Even this
black,
could be a
correct.
possibility. Okay,
Okay.
but this is, I'm just telling you, you're picking up from another bag. It's not a
Another bag,
wrong
okay.
experiment, right?
Okay, got it.
I can say that if you have taken a black one, you're going to a bag which has 3 white and 6 black balls. If you have chosen a white, you're going to a bag which has 4 white and 5 black balls.
Okay, got it.
Is that clear? Okay. In
Yes,
this experiment, I'm having dependency. Whereas in the tossing a coin twice, I did not have dependency. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So this gives us the notion of conditional probability. Now, when we talk about conditional probability, it is the probability of an event occurring given another event has occurred. So in our examples, we talked about what is the probability of head occurring in the second toss, which was your E, given head occurred in the first toss. Is that right?
Yes, ma'am.
Okay. So in a sense that F is head in the first toss. What are the outcomes of F? HH, and HT. Agreed? Head occurring in the first toss is HH and HT.
Yes.
Now I'm asking E is, what is the chance that head is occurring in the second toss given head has occurred in the first toss? This is the reduced space now I have here, right? What is the chance of head appearing in the second toss given head is? This is 1 by 2. Would you all agree?
Yes, ma'am.
Which is nothing but probability. So if you look at it, I can depict it this way. This is my set F. Okay. Now, given F has occurred, what is the chance E has occurred? That would be this shaded portion to the total F. Would you all agree with that?
Yes, ma'am.
The shaded portion is E intersection F. So it is probability of E intersection F divided by probability of F. That is what probability of E conditioned on F is given by. This is conditioned on F. This is not division. This is standing for condition. What is the chance of E appearing conditioned on F appearing? Is it clear? This is the definition of condition probability. Okay. Now, just as I had an addition rule which said probability of E union F is probability of E plus probability of F minus probability of E intersection F, from my definition of conditional probability, I can write probability of E intersection F is probability of E conditioned on F into probability of F. Would you all agree with me? I just multiply these two, I get this. This is the addition rule, which is the probability of union. The probability of intersection is probability of E conditioned on F into probability of F. Till here, is it clear?
Yes, ma'am.
Yeah. Right. Now, if E is conditioned, suppose I'm talking of two events and I know that E is independent on F. So intuitively, what is probability of E conditioned on F? F has nothing to do with probability of E. So the probability of head in the second toss is irrespective of whether I had a head in the first toss or not. Would you all agree that if two events are independent, probability of E and F, probability of E conditioned on F is the same as probability of E because F has no bearing on the probability of E. Would you all agree with it?
Yes, ma'am.
Yeah. Is that clear? So
Yes, ma'am.
what happens when I have two events? If they are independent, probability of E intersection F is probability of E into probability of F. So typically what happens is I know that this is my multiplication rule. That is probability of E intersection F is probability of F into probability of E conditioned on F, right? Now, suppose E and F are independent, then I know this probability of E conditioned on F is probability of E. So you can see that probably that when I have independent events, the probability of the intersection is product of the probability. Don't confuse this with the addition rule, which says that if E and F are mutually exclusive, what is probability of E union F? When they are mutually exclusive?
PE plus PF.
So when they are mutually exclusive, the probability of union is addition of probabilities. When E and F are independent, the probability of intersection is a multiplication of probability. So this is what we refer to as the addition rule. This is what we refer to as the multiplication rule. Is this clear?
Yes, ma'am.
Yeah. Now let's look at a very important theorem, which is called Bayes theorem. And I'm going to motivate that with this example. Okay. So suppose I have three manufacturing plants, which are giving shock absorbers to a certain company. Okay. So now you can see that suppose I'm getting 100 of these shock absorbers. How many are coming from A? If 100, suppose 100 is the total number of shock absorbers coming to this automobile manufacturer, how many of them are coming from A?
20.
20. So let me put this A, which is 20. Okay. How many are coming from B?
30.
30. How many are coming from C?
50.
50. So this is C, which is 50. Till here is it clear? Okay.
Yes, ma'am.
Ma'am, can I
Now
ask?
imagine that yeah.
Ma'am, can I ask one doubt? I mean, I was stuck up with mutually exclusive and independent event. Conditional
Yes.
probability occurs when the events are not independent, right, ma'am?
No, conditional probability can occur whether they are independent or not independent. If the events are independent, that is, if E is independent on F, probability of E conditioned on F is same as probability of E. That is what we say. See, conditional probability is what is the conditional probability of an event happening given something has happened. Okay, so what is you answer? What is the probability of a sum of 7 happening given first toss of a die? What is the chance of event 7 happening? Sum of 7 happening?
Sum of 7 is
1 by
I
6.
can have a 1, 6, 2, 5. It is 6 by 36.
6 by 36. Yes, ma'am.
Which is 1 by 6.
Yes.
Okay. Now this is independent of what my first toss was. That's what I'm trying to say.
Okay.
Is that clear?
Yes, ma'am.
What is, okay, let's look at the toys. What is the chance of head on the second toss given head in the first toss? What is the chance of head in the second toss? I'm having HH,
1 by
HT, TH, and TT. Okay. What is the chance of head in the second toss happening? Given that head in the first toss. So given head in the first toss is your event F, which is HHHT. Agreed?
Yes, ma'am.
Okay. What is the chance of head in the second toss happening here? This is 1 by 2 only, right? Because there are only 2 outcomes.
Yes, ma'am.
Right? So would you all agree that this is 1 by 2?
Yes.
Right? What is the chance of head occurring in the second toss? That is also 1 by 2. It is independent of whether you had a head in the first toss or not. That's what I'm trying to say. It is independent of this thing.
Okay.
Is it clear?
Yes, ma'am.
So the conditional probability and independent. See, one thing which you all need to understand is the following. When I have two events which are mutually disjoint is not the same as independence. Mutually disjoint, mutually exclusive, sorry, or disjoint event is not same as independent event. When I have mutually exclusive, probability of E union F is probability of E plus probability of F. When I have independent events, probability of E intersection F is probability of E into probability of F. Is that clear?
Yes,
Yeah?
ma'am.
Okay, this is what we need to understand. Now coming back to this example, okay, I have A, B, C. I'm getting 100 units. 20 come from A, 30 come from B, and 50 come from C. Till here, is it clear? Okay. Now I'm mixing all of them up. Out of this, I have a certain percentage which is defective. So whatever I have in the shaded region is defective equipment. Is this clear? Let me draw it again for clarity. Let me 1 second. Let me draw this again. So see, suppose I have this. 50% is coming from C, 20% from A. This is 20, this is 30, this is 50. Till here, is it clear? Okay. So imagine I'm getting shock absorbers from these 3 plants, and I got it in my company, and I know that there is a percentage of defective equipments in this 100 shock absorbers. That is what I am shading here. What is the shaded region? This is the defective shock absorbers. Is that clear?
Yes, ma'am.
Okay. Now, what is this shaded region? Just describe what is the shaded region. This shaded region.
Defective.
Defective and from A. And from A. So, would you all agree that I can write that as defective and from A, D intersection A?
Yes, ma'am. Yes, ma'am.
Now, what is this? This shaded region.
Defective item from the
Defective and from B, right? Now, what was this? This is defective and from C. Agreed? Now, this and this are mutually exclusive. They are disjoint. This region, which I'm calling as 1, this region 2, and this region 3 are mutually exclusive.
Yes, ma'am. Yeah.
So, this D, which is a defective item, can I write it as probability of D intersection A, union D intersection B, union D intersection C?
Yes, ma'am.
Yes, ma'am.
Right. So again, if I'm from an addition rule, this is probability of D intersection A plus probability of D intersection B plus probability of D intersection C. Would you all agree? Addition rule, nothing but that.
Yes, ma'am.
Yes, ma'am.
Agreed. But then from my multiplication rule, I know that probability of D intersection A is probability of D conditioned on A into probability of A. This is my multiplication rule. Just go up 1. What is my multiplication rule? My multiplication rule says that probability of E given F is probability of E intersection F. That is what it says, right? Probability of E intersection F is probability of F into probability of E conditioned on F. Agreed? So what would probability of D intersection A be? It would be probability of A into probability of D conditioned on A. Agreed?
Yes, ma'am.
Yeah. So would you all agree with me that I can write this probability of D as probability of D conditioned on A into probability of A plus probability of D conditioned on B into probability of B plus probability of D conditioned on C into probability of C?
Yes, ma'am.
Okay. This rule is what we call the law of total probability. Okay. That is, I know that I have 3 mutually exclusive sets. What are the 3 mutually exclusive events? Can a shock absorber come from both A and B simultaneously? One shock absorber, can it come from both plant A and plant B?
No.
So it can come either from A or from B or from C. So A, B, C are mutually exclusive. Agreed?
Yes.
Yes, ma'am.
And this defective, it can be, I can have a defective and it is from A, or I can have a defective and it's from B. I can have a defective and it's from C. Correct? A defective can be from A, or it can be from B, or it can be from C. Agreed? Yeah?
Yes, ma'am.
Right. Now, what is probability of D conditioned on A? What is this 3%? It is probability of defective items given it is from A, right? That is what I have. Agreed? What is this 3%? Records show that the percentage of defective items produced by A is 3. So how can I write it? What is the chance of it being defective? Given it is produced by A is 3%, which is 0.03. Agreed? Similarly, what is probability of defective given it's from B?
0.02.
0.02. What is the probability of defective given it's from C?
0.01.
0.01. Till here, is it clear?
Yes, ma'am.
Now, do I come to this formula? Do I know what is probability of D given A? 0.03. What is probability that I pick up a sharp observer at random? What is the chance it came from A?
20%.
20%. So this is 0.03 into 0.2. Would you all agree? Plus, what is probability D given B? So I have this as 0.03 into 0.2 plus a 0.02 into what is probability of B?
0.3.
0.3. What is the probability of D given C is 0.01. Probability of C, it is 0.5. So the first question is, what is the chance that a randomly chosen shock absorber installed by a manufacturer is defective? It is the sum of these probabilities. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So now what the Bayes theorem says is, what is the probability? Suppose I am mixing up all these 100 shock absorbers. I pick up a shock absorber at random. What is the chance it came from A?
20%.
I have 100 shock absorbers. I'm mixing all of them together. I'm picking one at random. What is the chance it came from plant A?
20 by 100?
20 by 100, 20%, right? 0.2. What is the chance it came from B? 0.3. What is the chance it came from C?
0.5.
0.5. Till here, is it clear?
Yes.
This 0.2, 0.3, and 0.5 are what we refer to as prior probabilities. That is, I'm picking up one shock absorber as random, and I see that, okay, what is the chance it comes from A, B, and C? Now I'm giving some extra information about what you have picked up. I see it is defective. Okay? I see that whatever you have picked up is defective. Earlier, what was my probability of A? It was 0.2. Probability of B, it was 0.3. Probability of C was 0.5. Agreed?
Yes, ma'am.
Right? Now I pick up a shock absorber. I notice it is defective. I want to know what is the chance it came from A. Is this clear? I'm conditioning. So what is the event? See, earlier when I just picked up a shock absorber and I wanted to know what was the probability it came from A, it was an unconditional probability, right? There was no condition. I picked up a shock absorber and I saw that the probability it came from A is 0.2. Till here, is it clear?
Yes, ma'am.
Now I am noticing that the shock absorber is defective. So I'm conditioning it on the event that it is defective. Now I want to know what is the probability it came from A. Would it be the same or would it be different? That is the question. Is that clear?
Yes, ma'am.
See, what is the probability that the part came from manufacturer A? That is 0.2. Now I'm asking, given that the part was defective, so I am asking for what is this posterior probability. Is this clear, please, the question?
Yes, ma'am.
Now, from definition of conditional probability, this is probability A intersection D by probability D.
Yes.
Right? So if you go back, okay. So initially, I had probability of A is 0.2, probability of B is 0.3, probability of C is 0.5. Now I pick up an object and I find it is defective. I want to know what is the probability of A given D. By definition of conditional probability, this is probability of A conditioned on D into probability of D. Till here, is it clear?
Yes, ma'am.
What is the numerator? The numerator is nothing but probability of D conditioned on A into probability of A. Now the denominator is what we just found out, right? It is probability of D conditioned on A into probability of A plus probability of D conditioned on B into probability of B plus probability of D conditioned on C into probability of C. Agreed?
Yes, ma'am.
Yeah. Now, do I know all the terms? What is probability D conditioned on A? What is the chance that a shock absorber from A is defective?
0.3.
0.03. Probability of A is 0.2. What is the probability of D conditioned on B?
0.02.
0.02. Probability of B is 0.3. What is probability of D conditioned on C? 0.01. Probability of C is 0.5. So I can find out this entire thing. What is the probability that the part came from A given the part was defective? Okay. That is what is called Bayes theorem. What Bayes theorem says is, suppose I have a set of mutually exclusive events, F1, F2, say Fk. Okay, these are mutually exclusive and I have an event E. Okay, I'm just extending this to K events. Then this probability of E is probability of E into F1 plus probability E intersection F2 plus probability of E intersection Fk. Would you all agree? Mutually exclusive events. E intersection F1 is this. E intersection F2 is this. These are all mutually exclusive things. Probability of E is this. Now from definition of conditional probability, this is F1 E conditioned on F1 into probability of F1 plus probability of E conditioned on F2 into probability of F2 plus probability of E conditioned on Fk into probability of Fk. Till here, is it clear?
Yes, ma'am.
This is what we refer to as law of total probability. Now I know what are the prior probabilities of F1, F2, Fk. I know probability of F1, probability of F2, probability of Fk. These are what are called prior probabilities. I want to know what is probability of Fj given E. This is nothing but probability of E given Fj into probability of Fj by probability of E. Probability of E I get from here. I know what is this. And this is what is called the Bayes theorem. So you have a lot of applications wherein you will be when you are asked to apply law of total probability. For example, let me give you one thing which you can do it on this one. You all have heard of a game show called. Let me ask you this game show thing. Suppose there are 3 doors. Okay, there is a car behind 2 doors and there is a goat behind the car behind 1 door and there is a goat behind 2 doors. Okay, is the question clear? I do not know. I am asking you to choose any one of the doors. Suppose you have chosen this door, D1. Okay, what is the chance that you would have a car behind door 1? I'm saying there's a goat behind 2 doors and there's a car behind 1 door.
1/3.
1/3. Agreed? Okay. Now this problem is what is called the Monty Hall problem. You can do a Google search and you can find out what is this Monty Hall problem. Suppose I ask you to choose a door and you choose D1. What the game host does is, he opens a door and shows a goat. Okay. He shows a goat. Now he says that you can swap your choices. That is, if you have chosen this door, you can choose this door. Would you swap your choice? Is the question clear? See, whatever door you choose, he is going to open a door and show you a goat. Because the goat is there in one of the other two doors, right? He's not going to open a door and show a car or something. And he gives you the chance to swap your choice. The question is whether you'll swap your choice or not. Is the question clear?
Yes, yes, madam. So we will not choose, madam.
You'll not choose. You'll not swap.
Yeah.
Why not?
May or
There
may
should
not.
be some.
We already.
No, you cannot tell that to the host now, may or may not. You should either swap your choice or you should not. When would you swap your choice?
If the known goat is instead of goat, it's a boat means we can choose.
So the thing is, what was the chance of you winning a car earlier?
It was 1 by 3.
It was
Now
1 by 3.
It was 1 by 3. Now,
Now
would
it
you
is
all
1 by
agree
2.
that if the chance of you winning a car, given that you know that there's a goat here, okay, if this is higher than 1 by 3, then you would swap the choice? Car, the door, would you all agree? See, the chance of D2 having a car, given that there is a goat here, if that is greater than 1 by 3, would you swap the choice or would you not swap the choice?
swap the.
You would swap it.
Swap
So
the
this
choice,
is how
ma'am.
you can apply. I'll just leave it as a food of thought. Okay. It's a very interesting problem, but it is a great application of Bayes' theorem to tell that people will always swap their choices. Okay, because the probability would, you are getting some more information about the goat. Okay, and you can, if you are all interested, you can just check as to how this Monty Hall problem has been solved using conditional probability. But the key thing that here we need to know is how we are first finding the law of total probability. The main thing we need to understand is I have mutually exclusive events. So for example, always we say that people are infected, not infected. Those are mutually exclusive. All these examples where you're talking about pass, fail, again, mutually exclusive. A person who has chosen two sports and things like that, again, mutually exclusive. So you need to identify what are the mutually exclusive events and what are not the mutually exclusive events. Is that clear? So in summary, what all have we learned today? We have done, so for the quiz, what are all the topics? We started with basic counting principle. Here we again reviewed what was the addition principle and the multiplication principle. Always remember, whenever you have an or, it would be an addition. Whenever you have an and, it is a multiplication. That is the same thing when you applied the addition rule of probability and the multiplication rule of probability. Permutations, we looked at permutation of distinct objects, of non-distinct objects with, without repetitions, and circular permutation. It is very important for us to understand where to use a permutation and combination. Look at whether the order is important or not. If the order is important, then you use a permutation. If the order is not important, use a combination. Then we moved on to probability. We first need to understand what is a random experiment. The things that we need to know is how to describe the sample space of a random experiment. And then from the random experiment, define the events. We went to the axioms of probability. We introduced what was the addition rule of probability. Then we introduced conditional probability and gave what was the multiplication rule. Then we introduced the law of total probability and we looked at the Bayes theorem. To understand conditional probability, we use the concept of probability trees where we illustrated what were the probability of total probabilities. For example, if I go back to the probability tree, okay, in this case, I know in this probability tree, the probability of H2 intersection H1 is nothing but 0.25. Okay, probability of getting ahead in the second toss and ahead in the first toss is 0.25, 0.5 into 0.5, which I know is the same as 1 by 4. Okay, whereas here I know in this example, probability of getting a black ball in the second toss and a black ball in the first toss is nothing but probability of getting a black ball in the second toss conditioned on black ball in the first toss into black ball in the first toss. They are different. So that is what I can see 6 by 9 into 3 by 7. I get a probability. Always remember the final thing, it will all add up to 1 because probability of sample space is 1. With that, I think we have, so you can see that this is the probability of B1 intersection B2, which is 3 by 7 into 6 by 9, 3 by 7 into 3 by 9. And this is nothing but probability of B2 given B1 into probability of B1. This is probability of W2 given B1 into probability of B1. This is probability of B2 given W1 into probability of W1. This is probability of W2 given W1 into probability of W1. That's how I've got it. This adds up to 1 because the sample space of getting a blue and a black ball. I think with that, I have completed anything. I'll be happy to take any questions. We have about 15 minutes left. I can take up any questions. Quiz 2 syllabus. Prashant, someone is asking about the syllabus for the quiz 2.
Yeah, so quiz 2 syllabus we have already mentioned. So it's week 5 to week 8. The things whatever we have discussed in the lectures.
Yeah.
So it's a week 5 to week 8 for stats
It's
one
week
course.
5 to week 8, right?
Yes, ma'am. Yeah.
For all subjects?
No, it's for just stats one course. So it depends on for other courses also. So it's
Yeah,
for
we are only
stats one.
dealing with statistics 1. For statistic 1, the syllabus is week 5 to week 8. And that is what we have reviewed today. It starts with counting principles, probability, axioms, and the conditional probability, and up to Bayes theorem. Am I right, Prashant?
Yes, ma'am. Yes, ma'am. This is the syllabus.
Yeah.
Madam, this summary is shared, so it will be helpful for us.
Pardon?
The summary is the summary of this presentation. So this is
I will share the presentation. Prashant will share it with you. I'll give it to Prashant and Prashant will share it with all of you.
Thank you, madam. Thank you.
Yeah.
May I ask?
I mean, permutation and combination, how can we determine whether the given situation is simultaneous or not?
What do you mean by simultaneous?
There were questions in EMQ that there were a situation given and it was asked that it is simultaneous.
Yes. Sorry to interrupt here. So Tushar, that is something we can discuss in our instructor session. Okay. So today's session is just about revisions of these concepts.
Yeah. Okay. We are not taking specific questions here. Okay?
Yes.
I have a doubt. Can you hear me? Is it fine?
Mm-hmm.
Yeah, good evening. When it comes to permutation, you are talking about the orders, and we were also talking about the circular permutation. So when it comes for the same, I mean, there is no distinct objects. So if it's identical object, then there is no whether it's a linear or circular permutation, it doesn't apply there, am I right?
No. See, for example, if you are talking about, are you able to see my screen?
Yes, ma'am.
Right. So suppose we are putting, I have 5 blue beads. Okay.
Yes, ma'am.
And I'm putting it in a line. There's only one way of arranging. It is either B1, B2, B3, B4, B5, or B1, B3, B2, B4, B5. It's the same thing, right? So this is where we talked, it was n factorial by p factorial, where p is 1, n factorial by n factorial. It is only one way of arranging. Clear? Is it clear?
Yeah.
Okay. Now, if I had this blue beads and I'm putting it in 4, that is, I'm fixing one blue bead, the other blue beads, because they are the same thing, okay, and they are not distinct. So in the circular, we did not remove them into distinct and indistinct. We just looked at distinct objects. That's why we said it was n minus 1 factorial by 2. Would you agree with that? n minus 1 factorial if clockwise and anti-clockwise are the same. Others it's n minus 1 factorial by 2 if they are the same. Clockwise and anti-clockwise are not the same, it is n minus 1 factorial. If clockwise and anti-clockwise are the same, it is n minus 1 factorial by 2, right? But if I have all of them are the same, I would agree with you. There's only one way of arranging all of them, whether it is circular or, but if they're not the same, it would differ, the linear and the the circular permutation. I hope I answered your question.
Yes, ma'am. Because when it comes for the, you also discuss about the clockwise and the anti-clockwise. So I also want to know, because that's the reason. Because here,
see, suppose the simple thing is, if I'm making 3 people sit in a line, A, B, C, how many ways can I do it? In a line.
Yeah, that will be ABC and
it
C,
is 3 factorial,
3
right?
factor, yeah.
Right? But if I'm making them sit on a table, how many ways can I do it? That would be 2 factorial, right? ABC, it would be 2 factorial. If it's A, it is ABC or it is ACB. Agreed? Clockwise and anti-clockwise are not the same. If clockwise and anti-clockwise are the same, it would be one way, right?
Yes.
That's what we are looking at, where these are distinct people. So again, if they're not distinct, it would change accordingly. Is that clear?
Yes. Yes. Okay.
Yeah.
Thank you.
Yeah.
I'm looking at the question. It is at times difficult to judge whether it is conditional probability or we have to go for Bayes theorem. Okay, is there any clue sort of thing you can give?
See, conditional probability is always, you remember, I would always suggest you read the problem very carefully, okay? Wherever they're asking, for example, let's go back to this problem itself, where I'm talking about this manufacturing thing, okay? Without looking at math, don't about math or anything, you said conditional probability or Bayes theorem. I would first, even the first thing is there's nothing like conditional probability or Bayes theorem. Okay. Now, if you look at this, okay, this will explain all the possible things. Now I have, what is the event I'm having here? I have a company which is having different shock absorbers, and the random experiment is to pick up one shock absorber at random. Is that clear?
Yes, ma'am.
So what are the possible outcomes of this event? That shock absorber could be from A, it could be from B, it could be from C. Would you all agree with that? My sample spaces, the shock absorber could be from A, it could be from B, it could be from C. Till here, is it clear?
Yes, ma'am.
A, the event could be shock absorber from B, event could be a shock absorber is from C. What is the probability of A? That is given to be 0.2. This is 0.3. This is 0.5. Till here, is it clear?
Yes, ma'am.
Right. Now I have a defective item that could be from A, it could be from B, it could be from C. Defective given it's from A, defective it's from B, defective it's from C. So this is, I am finding out what is the probability of defective given it is from A. So there I'm conditioning it is from A. Whereas when I'm talking of probability of defective, this is unconditional. I'm not conditioning it on anything. I'm picking up an item. I'm asking what is the chance it would be defective. Do you get it? Now, when can a item be defective? It could be defective and it is from A, or it is defective and it's from B, or it is defective and it's from C. This is how we got the probability of defectiveness. And for this, we use the notion of addition and multiplication rule. Is that clear?
Yes, ma'am.
Right? So given the context of the problem, we need, and Bayes theorem is whenever you want a posterior. For example, I'm picking up an item, I observe it is defective. Now I want to know what is the chance it came from A. See, earlier the best way to understand this is, suppose I am mixing up all the shock absorbers I get from A, B, and C. I pick up an item. I want to know what I want to, first of all, I'm picking up an item. I'm asking what is the chance it could be good or it could be defective. Would you all agree with me?
Yes.
I'm asking first what is the chance it is defective. For that, I am using the law of total probability. Okay. Now I am asking, I notice it is defective. I want to know what is the chance it came from A. That is where I'm using Bayes' theorem. So breaking it down to different items, finding out what is prior, what is posterior, what is required would help you. So break it down to smaller portions. Is it clear? Identify what are the mutually exclusive events. Identify what is the conditional probability that is given. And then you can solve it using Bayes' theorem. It comes through practice. Okay. Yeah, I hope I've answered your question.
Yes, yes. Thank you.
Any more questions? Okay, if there are no more questions, I think I'll close it here. I wish you all the very best for your quiz too. Okay, take care and good night, everyone. Thank you. Thank you all. Yeah, thank you all.
Thank you,
Thank you,
ma'am.
madam. Thank you.
Thank you all. Yeah.
Thank you, ma'am.